So last time, what did we do? We basically shows how to get max flow using push Relabel algorithm, right? It has this kind of running time, mn, on unit capacity graph. And what about capacitated graph? What's the running time? mn, say again.
I mean, the H stands for...
mh, and then what?
There's a log.
There is log n there, yeah. And h is we're gonna set it to be n for max flow, yeah. So that's for capacitated graph. Okay, that's what we learned last time. And the goal today is to go beyond mn, like make it faster, at least in some graph. Okay, but we're gonna pay some approximation. Okay, good. So in particular, what we will do is that we'll see how to compute approximate bipartite graph, which I can recall that is some instance of max flow, like it's special case of max flow. And you'll see how to do it in basically linear time, m over epsilon. Yeah. So if epsilon is constant, this is linear time. And also we're gonna see how to compute approximate max flow on DAX in something like n square. We saw something like this for approximate shortest path, right? And it's gonna be similar. Yeah. Okay. So what's the idea here? The key idea is that if you recall, in push Relabel algorithm, we call type H data structure. In the type H data structure, each edge has some weight. Previously, we set the weight of every edge to be 1. And today, we will not do that. And we'll see that it helps. Okay. So just not use all one weight, edge weights. Okay. But so let me recap a lot of things first. Yeah. We need to build it up from the ground up. Okay. So first, recall type H data structure and approx type H data structure. Right? This is just old stuff, but I just want to recall. So what do we have? We have the graph with some edge weight. Okay. And at least in our class, we assume the weight to be non-negative. Yeah. And there's going to be some label on vertices too. Label that maps vertices to numbers up to h. Okay. Maybe in your homework you'll see how to handle negative weight. But in class so far, we just assume non-negative weights. And we're going to maintain active edge set. And anyone recall what's the intuition about this active set? What's the intention about this active set?
They're all tight.
There's basically the tight edge. Okay, what's tight? What's tight?
It is stretched and relaxed at the same time.
So if the edge U is U and V, you have level U and level V. What's the relationship between level U and V?
Equals the distance.
Say again?
The distance.
The distance. The distance between U and V is what?
Is level U minus level.
Yeah, it's W.
Assuming that U is higher up.
Right, yeah. So basically, it's basically this direction. U is more than V by this much. Right. That's what it means to be tight. Okay. Yeah. Okay. Good. That's we kind of want active guy to be this edge that is tight. Yeah. Okay. Okay. Now there are updates to the input. Well, you can increase the height, relabel, okay, of relabel vertices. When this node is not tied by any other guys. Okay. And you can delete an edge. You can insert relaxed edge. Okay. That's the update that you can do. And yeah, for tight edge data structure, we want that all edges are always relaxed, no overstretch. And the active guy is just the guy that is exactly the guy that are stretched, which means it's tight. Okay. And can you recall what's the invariant for approx guy? What about approx tight edge? How do we relax this?
We allow some leniency in the stretch. So if we guarantee that if an edge is stretched, it's at least 1 minus epsilon stretched. And once it's at least 1 stretched, it has to be, it's active if it's...
Yeah, what you kind of say that is like, for active guy, it might not be if and only if it's 1 stretch, right? But it should be kind of basically 1 stretch. So maybe like this is kind of 1 plus minus epsilon stretch. That's the idea. What about this? Like how do we relax this first one too? What is the relaxation to the first one for all edges? Yeah.
So like 1 plus epsilon relaxed.
Yeah. Now this one can be 1 plus epsilon relaxed. It's like it can be overstretched by a bit. Okay. So that's exactly what we have. It's 1 plus epsilon relaxed for all edges. And this is active if and only if it's basically 1 plus minus epsilon stretch. But specifically, if it is 1 plus epsilon stretch, really stretched, like quite stretched, then it's active for sure. And if it's active, then it's at least 1 minus epsilon stretch. Okay, that's the okay. So yeah, keep this in mind that like okay, when you maintain this tight edge data structure or approximately tight one, like this is kind of what the guarantee that you always have. Okay. Okay. What's the running time of tight edge? If U is the number of edge update, then yeah. The running time is just something like mh plus u. And for the approximately type 1, the running time is kind of more relaxed. So this is like nh here. Maybe I just write nh, which is better than mh. And this one, instead of mh, is like, which is to pay h per edge. We pay less per edge. Because it's like if the weight is big, then this is like you pay less than h per edge. So that's better. Okay. Okay. Anyone recall like what's the idea of this approx tight edge data structure? How did we make it faster?
We just, instead of doing like 1 level at a time, we did jumps proportional to the weight of the edge. Times the weight of the edge.
That's quite correct. Like every node still like increase the level one by one. Like here, every node here just increase the level. Like that's why you get NH. You increase level one by one. But what it kind of related to what you said is like for every edge you pay less often. That is, for every edge, UV, if the weight is like WE, then we're gonna check, we're gonna probe this edge if it should be active or not, only once in a while. What's the frequency? How often we should probe this edge?
It's the epsilon times the weight.
Epsilon times the edge. That's the, like, basically once the level of this guy changed by epsilon times the weight, that's when we check. Because it doesn't matter, like if it changed by epsilon times the weight, like things doesn't really change how much this edge stretch. That makes sense? Okay. So it's okay to just like check whenever the endpoint here increase the level by epsilon times the weight. That's when we probe it. That's why like we probe this edge every epsilon times the weight. And we need to probe it h over this. Okay? Okay. So yeah, try to record this. So yeah. Okay. So that's tight edge data structure. Let me recap push Relabel too. Okay. So we have a graph, right? We have a source sink function. And let's say now that I gonna have like a weight to both forward one and backward one. Why do I have the weight for backward one? Because at the end, like in the algorithm, we will work with residual graph, and residual graph will not have just the forward edge; it will have backward edge too. So we assign the weight to the backward one as well. Okay. And the algorithm push Relabel algorithm just do this, right? The thing that we learned last time. It's just you start with every level to be 0, start with empty flow, and then we maintain the tight edge in residual graph. This is tight edge, like tight edges of residual graph, and only the guide is tight. Okay. But on what weight function? It's on all one weight function. And what we do is just we keep like fighting the guy that is not dead yet and it has access, and keep like either push flow, or if you cannot push flow because there's no active edge out of it, then you increase the level. Okay. So try to imagine this kind of mentally imagine this process in your head, right? Like find a guy that with access. If there is some active edge, push. Otherwise, Relabel. That's the yeah. Okay. All right. And the key point of this thing, yeah. What, like if I just say in one sentence what push Relabel is trying to do, it's just that it tries to make access and saturation sink far away from each other. In what graph? Not in original graph, in residual graph. That's what it does, right? Why? Because like when does it end? It ends like you start with like 0 and level h. At the end, like all the excess is here, and all the sink that is not saturated yet is here at level 0, and this is far away in GF. That's what it does. That's the whole goal of this algorithm. Okay. And it just try to do this in the most straightforward way. Okay, so to be more precise, if I let this set here to be this what set of vertices with access after setting f, and this is just a guy with like a unsaturated sink after setting f, then push the label, justify a preflow that respect the source and sink such that the distance in residual graph from access to sink is at least h. Right? It's really just from this picture here. Okay. We have this thing. Okay. This is just, what is this again? Like just if you take any S and T, like the S is access, T is a sink, then look at any path from S to T, the size of the path here, the number of edges in the path here is big. Okay. Questions about this? Okay. Like because why? Like more precisely, like the level is like this, right? Everything that is the excess has level h. The sinks all have level 0. And what we know is that we know that the level for every node lower bound the distance to sink to the guy that is like with level 0. And try to see this intuitively, because should be intuitive, because like all edges are relaxed, right? If all edges are relaxed, then there's no way to like. It's kind of. You see. Like imagine that this is like level 0 and this is like you try to push like increase level of nodes, right? But if all edges are relaxed, no edge is stretched, then there's no way that you increase the level by more than like the length of the shortest path. The length of the shortest path here, like if this is shortest path, then like the length of the level of V cannot like exceed this shortest path. Otherwise, the shortest path would be stretched. So I want you to like really see this intuitively. Is this intuitive to you? Like question about this? Okay. Okay. And what we did last time is when we want maximum flow, we just set h to be n+1. Why did we do this? Why n+1 is a good number?
All the distance has to be less than or equal to n, so we set this to n+1. Then there's like
if the distance is more than n, it's n+1. It just means that there's actually no path at all. There's no way to go, right? So if distance is more than n, it's just that there's no path from access to sink. That is, there's no shortest path, no opening path. If there is no opening path, just means that f is maximum. Okay. And the running time of the whole algorithm here is basically the time for tight edge data structure. Like each of the step here, like is kind of dominated by the time to maintain this tight edge. Okay. You can like find the active guy like just by maintaining some queue. That's kind of simple. So the whole thing is just type H as a structure. What's the running time for type H as a structure? It's something like mh plus u, the number of updates. Okay. But in unit capacity graph, we see that the number of updates is something like mh too. Why? Because the number of updates is basically the number of push. Every time we push, we update something. But every push is saturating in unit capacity graph. And we show that number of push is mh. Number of saturating push is mh. Okay. So that's why the running time is mh. We learn also 3 push Relabel because such that number of number of unset push actually can be as big as mh square, but we don't want to pay this. But there's a way to avoid this using Lincoln tree or top tree. Okay. And we learned this. Okay. Good. But for today, let me assume unit capacity graph just for simplicity. We don't want to talk about 3 push Relabel because we can do it, but it's just complicate things. Let me introduce a new idea on just unit capacity graph with basic push Relabel. Okay. And what we're gonna do, is to just analyze push Relabel when the weight is not all 1. Okay. And then we see the good application that I list in the beginning. Okay. So let's just consider the same algorithm here. It's just exactly the same. The only difference is the thing that I highlight in red. It's the same push Relabel algorithm, but I choose like a arbitrary weight function here. Weight function from like for each forward and backward edge. Okay. This is a weight function W. Yep.
When you say arbitrary, like they have no bearing on like anything to the graph. They're just kind of like random, or
So like we will set this guy to be something specific soon, but right now just think of it as something arbitrary.
okay, cool. Got it.
Yeah. Okay. For example, like the thing that you can think of right now is like maybe I set every forward one to be 1, but every backward one to be 0, for example. That's one example. We will use this. Yeah. So for concreteness, you can think like this. Okay. And this is just the same thing, exactly the same thing, except that we feed this weight function to type H as a structure. Okay. Good. And because type H data structure just works for any non-negative weight function. So this algorithm, at least is valid, right? It just work. The question is, what does it do? What is the guarantee? Okay. So what do you think? When the weights are all 1, what we say is that at the end, the distance, the number of hop from access to sink is at least h. Now, if the weight is w, what would be your guess? What's the guarantee? Any guess?
Does it need to be like the sum of the weights or something, or like something like that?
Yeah, maybe you say like, okay, we used to say that they are far in terms of number of edge, number of hop. Previously, like the number of edge from access to sink was at least h. But now maybe like, now that this is like an arbitrary weight, maybe now it's just the weight, the total weight is at least h. And that's exactly exactly what it is, like what it will give. I claim that you're gonna just get this, okay? This one, we just find preflow respecting the source and sink, such that this thing is big. We used to have that this is just like the all one weight. But here it's just that the distance from access to sink in residual graph with respect to this weight is big. Okay. So for every ST from access to sink, any ST path in residual graph have weight with respect to this W at least h. Okay. And why is that? Because you see, like we're gonna have the same structure of labeling. We're gonna have that every guys, we're gonna like, so you see like, we just keep doing this until you cannot do. Like, so at the end, all the access will have level h and all sink will still have level 0. Okay? So all the access have level h, all sink has level 0. Okay. And we still have this thing, right? The level will lower bound the distance in this weight function. And it's just this, we just use this weight function because the type H as a structure use this weight function. Okay. This lower bound the distance just because all edges are relaxed, like before. Okay. So if the sink are at level 0, all the access are at level h, they are far away, and so the distance is lower bound by the label. So it means that the distance from access to sink is always at least h, but this distance is with respect to the weight W. So it's really natural and like it's just the same, exactly the same proof. Okay, now I claim something about running time. I claim that the running time is just still like the proportion to the type H data structure. There's nothing new, but I actually claim that like U here is still MH. The number of updates to GF is still H. This is gonna be at least at most MH with some caveat, with some condition that at least like the sum of for each edge, the sum of its weight and its backward edge is at least 1. Okay. So why is that? Like, so I hope that everything here, like you should kind of be convinced. The only thing that is not, that maybe is not too clear is this part. Okay. So let me try to tell you. So, like U here in unit capacity graph, you're still gonna have that like U is at most number of push, and number of push is just number of saturated push in unit capacity graph. This is in unit capacity graph. Yeah. But we kind of need to bound the number of saturating push. Okay. And I claim that every edge will become saturated at most this many times. Okay. Every edge is saturated at most h over like the sum of the weight between the sum of the weight of itself and its backward one. Okay. But if that's the case, then it means that the total number of saturating push summing over all edge. Maybe I should write over all edge and the backward one, E in E union E backward. It's just this. Yeah. And it means that if this thing is at least 1, if the sum of the weight is at least 1, then this is at most mh. Okay. So like if you believe in this one, then you should see that this is at like you get this bound. Yeah. The bound here is true. Okay. Is the statement here clear? Not the proof, but statement. Okay. So now, why is this the case? Well, it's basically kind of the same, similar proof that we saw before. Okay. Suppose that UV here is saturated. If it's saturated, then it's removed from GF, right? And to even create this edge again, then you know that we need to send flow back to you. Okay. Only when we send flow back to you, then you recreate the edge UV. But how can we send the flow back to you? It means that the edge from V to U need to be stretched, need to be active. So it means that the level of V here, V need to be here, and the edge from V to U need to be active. So this is the length here is at least kind of the weight from V to U, right? It needs to be stretched to be active. The weight from V to U need to be like the level of V need to be higher than the level of U by this much. That's when it's active and you have a chance to send some flow from V to U. Okay. So now you create this edge from U to V. Like the edge from U to V is now kind of back. But to even send flow from U to V, again you need the edge from U to V to be active, which means that it's stretched. So the level of U here need to be here, and the length here it need to be at least like this edge from U to V need to be like stretched by W of U plus V. So in total, the level U must have increased its level by VU plus UV. Like, yeah.
I know we're bounding by like if the weights are greater than 1, but the nodes can't jump less than 1, right? Like a label.
The level cannot jump less than 1. Yeah.
So even if these weights are really small, they would still be stretched, I guess, farther than like if you had on like 0.2 and you jumped it, it'd be like I mean, pulled way more.
Oh, but you think like the weight is integer too. So it's like it's never like less than 1. It's either 0 or 1. It can be,
got it.
yeah. It cannot be half. Yeah. Okay. So if you think we saw like if you like this can be 0, so it just suppose that this is 0. It just means that like to send flow from V to U, you need V to be at the same level of U. Or like if it's now 1, you just need to increase this level to be strictly better, higher than U by 1, for example.
They're both 0, you can just keep going back and forth, right?
Yeah, exactly. That's the idea. Like if they are both 0, it might just go back and forth, and that's not good. And we exactly that. Yeah, good intuition. Yeah. Okay, so that's it. Okay, so to create, this is what I just said. To create this edge UV, you must send flow back from V to U. At that time, the level of V need to be more than level of U by this much. This is here. Okay, and then to push flow through UV must be stretched again, and so like the level of U, the new level of U, need to be more than the new level of V by this much. This is kind of here. And this total, like it means that you need to increase the level by the sum of these two. Okay. But you see, so basically to push flow through UV again, you need to increase the level by this much. But the level is bounded by H, so the total number of times that you kind of saturate this edge is just H over this sum. And that's why you get this bound. Okay, good. Let me go quickly through this too. We can talk about doing push Relabel with any weight function, but now we use approximately tight edge data structure. Okay. So we use any weight function here, but we allow some slack in tightness, epsilon tight. Okay, now here you need to tell me what do you think is the guarantee of this? We used to just say that without this, the distance from excess to sink is at least h in terms of W with respect to W. Now that we use approximately tight edge. Okay. What changed?
Yeah. Can we get a 1 plus epsilon approximation on the distance guarantees?
Exactly. Yeah. So why is that? So first, what's the level of the guy with excess? For the guy with excess, what's the level at the end? H. It's just at the guy with excess, we just say that it is. We don't stop until it has level H. This is the case for all guys with excess. What's the level for for the sink? For the unsaturated sink?
Still be 0. Yeah.
It's going to still be 0. The sink that is not saturated just remains 0 all the time. Okay. And what can we say about the lower bound? What's the relationship between the distance to sink or to the guy with level 0 for all v. What's this?
At most 1 plus epsilon times distance.
Exactly. Yeah. This is at most 1 plus epsilon height times distance. And again, like, yeah, if every edge is at most 1 plus epsilon height, like it's at most 1 plus epsilon, it's like every edge is 1 plus epsilon relax. You can stretch a bit more than the distance, but the stretch, like this, you should think like this is like this minus 0, like from 0 when you stretch b, it shouldn't be more than the distance, but with this slack, because you allow edges to be like 1 plus epsilon relax. It stretch a bit, but it's not more than this. Now, when you combine this thing together, right, you just get this. That the distance from excess to sink with respect to W is just at least h over this one. Okay? Good. And what's the running time? It's just the running time for approximately tight edge data structure, which is what? Which is this thing. Okay. So how do we see this? Well, like, good. This just follows from. Okay, this needs a proof a bit actually, but. Okay, one sec. This thing, you just see that this is at most sum over edges, right? And hash over this plus this thing backward. Okay. And this is just n hash. Okay. And this is basically the same thing here, but you have this epsilon here. Okay. Good. All right. But why we get this one? Well, like, let's see. It's basically like in approximate tight edge structure, you have this one, right? This one. This is epsilon tight. But I let you think, actually. It's like, okay. Maybe think like, how many times you need to probe? Like maybe think like, how many times you need to probe both U and U backward? Yeah. And the total time you need to probe them is something like 1 h over this one. Okay, that's how you get this. Okay, so my point is like, so maybe like we just state this one, but actually we can actually get this one. Okay, and try to think how. Okay, but now like you can see that the running time looks nice because it's potentially better than MH. This is just NH, and this is sum over all edges, right? But if this part is big, then it's better than MH. That's how you hope to improve upon MH. Okay, so that's like how we analyze push Relabel when you use different weight function. Okay. We're gonna exploit this soon. We're gonna use different weight function and get something better soon. Okay, but just before that, so far it's kind of just small extension of what we learned last class. Okay, so just before we go to the real application, let me tell you some basics about flow a bit more again. We need this. Okay, we need a concept of length of flow, okay? Or total length of flow. So you have a graph and you have a weight function, and let's say that F is a pre-flow of flow. Okay, and recall that the value of F is just the total amount of mass that you send from source to sink. Some mass from pre-flow might not reach sink, that you don't count. Some mass that reach sink, you count that. Okay. Now the new concept is total length. Okay. Total length of the flow is just this thing. I write W of F, which is just the sum of all edges, the weight of edge, this edge, times the amount of flow on this edge. Okay. So for example, if I have this graph and then let's say the weight are all 1 and the flow is 0 or 1. Let's say this is my flow. This is a kind of 0-1 flow. Then the total weight here is just 7. This total weight is just 7 because, just count the number of guys here, really. Okay. If it's longer, if this is long, then that increases the total weight. Okay. So it kind of measure how long in total, not just for one path. If it's just for one path, it's just the length of the path. But here's you measure the total number of edges that you use, basically. But now you can have this scale too, right? So if the flow along this is just actually 0.5, 0.5, 0.5, 0.5, then the total length along this one, you kind of scale it down as well. Okay, so this can be write in succinctly W inner product with F, but we don't need that. Yeah, it's just okay. Okay, so when this is a simple one, it just count the number of edges on the flow. But in general, it can be general. Yeah. Okay, now the average length is the total length over the value of the flow. Okay. So, for example, if this thing is have flow value 1 and the length is 10, and this one has flow value 1 and the length is 20, then the average length is 15. Because it's this over this. Yeah. If it's a pre-flow, you could have some path from S to somewhere else, right? So that will increase the length, but it will not increase the value. So okay. So just some intuition. Okay. Another basic thing is about sum of flow. Okay. So maybe think suppose that I have 2 flow. Let's say that F1 is a flow in H that like send from source to sink. Like let's say this is like F1. And then after I send F1, like this and this, then I get like residual graph. And here, like I assume that each edge has capacity 1. So when I use up some edge, when the flow goes through some edge, it just flip in residual graph. So this is my residual graph after I send F1. And residual source is what? This decreased to 2. This have the source now, 1, because I kind of just send up to here. So this is like excess of 1. The residual source here is 1 here. Residual sink decreased from 4 to 3. And maybe I send another flow F2. Maybe F2 is like this in this graph. So I just follow this path. Okay. And this flow will basically respect, oh sorry, I send this one, I send this one. So I basically send from this excess here and from this excess here to the sink. Okay. So this flow would respect this graph and the source and sink in this new graph. Now you can look at the sum of this flow, right? So the sum of this flow will basically be a pre-flow in original graph and respect the original source and sink. Okay. So that's natural because that's how we kind of define residual graph. We define residual graph so that when you find new flow in residual graph and add it up, then it becomes like a kind of the flow in original graph. So if I add F1 to F2, then in this example, what do I get? Well, like if I kind of add them up, then this edge kind of cancel, right? And basically, I get, I get this one and this one. This is F, which is F1 plus F2, right? And you can say that like it's just a flow in original graph, and the value would increase. Like just the sum of the two values. In this case, the value here is 1. The value here is 1. No, wait. The value here is 1. Oh no! I cannot send this flow. Sorry. This thing should have. Yeah. This thing should have this direction. So this flow actually is not possible. Wait. Sorry. No. Okay. So what's going on? Oh, sorry, good. There is another flow here. So this value here is 1, value here is 2. So the sum is 3. Good, yeah, checks out. Okay. So the value at the end here is 3. Okay, good. Okay. Now I can ask about what is the length, the total length of F. And it's going to be just at most the sum of the two. Okay, why is that? So actually, you can see that if there is no flow, if there is no cancellation here, for example, like here I cancel some edge, some flow. If there is no cancellation, then the total length of F would be just the same of the sum here. But now I cancel something, right? If I cancel, like if there is some flow cancellation, then that thing cancel, and it would reduce the total weight. So when it cancel and it will reduce the flow value, but on that edge, the length of this flow is like negative, positive too. So when the flow cancel, it kind of reduce the weight on that edge by something positive, by something non-negative. So it only decrease the flow, the total weight. Okay. So if there is no cancellation, you get this. But there can be some cancellation on some HE. But this cancellation will only decrease the total length because here I use the fact that the weight is not negative and the flow is positive. So you just remove something positive. Okay, good. By the way, if you want something to be like equals, you can define the weight such that the weight here is like kind of negative of the forward one, but you can check this. This just exercise. We don't need this one. Okay, good. So now we are ready. We are ready to talk about some new thing. Okay. So imagine this kind of graph where I want to send flow from S to T. And I want to send it fast. I don't want to spend mn time. I want to spend like maybe linear time. Okay. And so maybe this is the max flow. And this long path, this might be a max flow. But maybe like I don't even want to find this one because it's kind of long. Like all I want is just to find some flow that maybe as good as the black one. Okay, so that's like the motivation. Like competing, like this black one is short, and it kind of makes sense to just try to send 5 flow that is as good as the best short flow. That's the goal here. So here is a formalization of the problem. You have a graph. You have parameter D. And we want to find a flow, a pre-flow, such that the value is as big as the maximum flow, like F star. F star is maximum in this sense. It's just a maximum flow such that the average length is at most D. Just the guy whose average length is not too big is at most D, and take the guy is maximum. That's F star. So by average length here, I mean like when you take all one weight function, the average length of F is at most D. Here just count the number of steps. Just the normal version of length. Is this clear? The goal? Okay. And we're gonna get running time something like this time. So when D is small, this is fast. It's not mn. And here's the algorithm. It's quite short. We just first set the length of every forward edge to be 1, every backward one to be 0. And we just run push Relabel on this weight function. And the maximum height is more than D by quite a bit. More than D, like it's 2D over epsilon. So if epsilon is small, then like it's bigger than D by quite a bit. But if you think of epsilon as constant, it's just order of D. Okay. Good. And you see running time here is just md over epsilon, because we see that like the time for push Relabel, it takes like mh as long as the weight, the sum of the weight on both one, the sum of this forward and backward edge is at least 1. and h here is d over epsilon. So this is like md over epsilon. Okay. So running time is clear, but we just need to see why it's correct. So that's what I claim. The size of the flow is going to be as good as f star up to epsilon. Okay. And the idea in the proof here is kind of to treat the residual graph GF as your main graph. Imagine that you start your graph with GF, and then you try to send two flow in GF, one by one, and then sum them up. Okay, so imagine this. I start my initial graph H with GF. Okay. And well, this is GF, so the source is like residual source, and the sink is residual sink. Okay. But just think like you just start with this graph and this initial source and this initial sink. Okay. Okay. And then I first send some flow in this H. What's my flow? My flow is negative H, negative F. It looks a bit intuitive. It's like doesn't look like a good flow. Just basically, it has value negative, right? It kind of removes the thing that you have sent so far, but it's a valid flow in H, right? Because like if you send something like in this residual graph, you could send something backward, like just revert everything. That's the flow F1 that I send in H. And then consider like after sending this, I just send F2, which is F star. F star is sent in the residual graph, like in H after I send F1. Okay. What is this one, by the way? This H1 is just, yeah. What is this graph, by the way? There's something simple. It has a good description. So H is a residual graph, is JF. What will happen to H after I send minus F?
Is it just G again?
It's just G again, yeah. Just to understand notation. Yeah. It's just G again. Okay. But anyway, like thing like this, you have H, and you first send F1 and F2, and then F2. Then you just look at the sum of this flow. Let's say that this is F prime. It's a sum of F1 and F2. So it's this sum. Okay. And this then is like, it's a preflow in H. Right? Because I have two flow that I send some flow, and then I send the flow in residual graph. So the sum is a flow in original graph, which is H. Okay, good. And we know that the length of this flow is just at most the sum of the length of F prime is the sum of the length of the two flow here. Okay. What's the length of this guy? And the length of this guy. Okay. This one has a simple description.
Isn't it just 0 because it's just backwards edges?
Exactly. Yeah, like this guy, you see, is the flow in, like if it's not minus F, this is a flow in original graph, right? Which use only forward edges, but minus F. is a flow that only use backward edges. Backward edges have weight 0. This is 0. And what's the length of this guy? This only use forward edges because it's a flow in original graph. So this basically it's just equals to R1 of F star. But F star have small average length. So this is at most D times the value of F star. So this is basically at most D times F star. Okay. Good. We get this. Now let me suppose for contradiction that my F here is small. It's not as big as F star. Okay. It means that the value of F prime is just the sum of the two, right? The sum of the value of the two. Maybe I should write minus F, but this is minus of F. Okay. So this would be at least more than epsilon F star. Okay. So what we have so far is like we upper bound the total length, and we lower bound the value. So we get upper bound on the average length. The average length of F prime is then at most D over epsilon. Okay. So F prime, we get that the F prime have average length D over epsilon. But at the same time, what do we know about push Relabel? Push Relabel says that in residual graph, so first F prime is free flow in GF, right? This is like a free flow in GF, and it has small average length. But can you try to tell me why this seems like a contradiction? What's the guarantee that push Relabel say about GF? Like I said, push Relabel, like I just write PR of G with H equals this thing. What's my guarantee? Like it returns some flow here. What's the property of GF? The distance from access to sink is far. It's at least H far, right? Like access to sink is H far. This is a free flow in this that send from access to residual sink. And this guy says that it has, like on average, each flow that successfully sent have this length. But in GF, push Relabel just guarantee you that they are far. Like every path from access to sink are just far. Like much more than this one, like twice of this, right? So then it means that like that's contradiction, right? Like every flow path in F prime actually need to have length at least H, because every flow path from like in F prime just go from access to sink in residual graph, but in residual graph, push Relabel guarantee that like to go from access to sink, it takes at least H. That's impossible. Okay, questions? Okay. So now you see that what we get now is like what if I want to solve bipartite meshing? Okay, how fast can we solve this now? So let me recall bipartite meshing. So bipartite meshing is maybe this one, this graph, right? And we want to find some meshing, maybe like this. Okay. Some meshing. This is a meshing, so the edge, the disjoint edge, right? This is not maximum. The one here is maximum. Okay. We want to find maximum meshing. Okay. But we can actually model maximum meshing, bipartite maximum meshing as the flow problem actually. So you see that if I just add one node supersource here and just do it like this, then if I try to send maximum flow from S to T, that just corresponds to maximum meshing. Every flow from S to T corresponds to a meshing. Okay. I just write down the direction to be like this. Yeah.
What can the slope be fractional? If it's say half through the edge and half through the other edge, then how do you get them?
So you can assume that if you know actually that as long as capacity of a graph is integral, then max flow is going to be integral too. Yeah.
Is that easy to see?
You can see it, for example, from the proof of max flow min cut. For example, imagine that you know Ford Ferguson, keep finding augmenting path. When you keep augmenting path, keep finding augmenting path, there is no part of the flow. There is no time of the flow that is integral. That is not fraction. That is not integral. It's always integral. So there's always integral max flow. Yeah. So if you find integral max flow, that corresponds to bipartite meshing. Maximum bipartite meshing. Okay. But what's the average length of max flow in this graph?
3.
3. There's just 3 steps to do. Right. So D is 3. And if you want just to find approximate max flow in this graph, then just do this in times 3 over epsilon time. So that's how you solve this problem fast. And in general, if you have a DAG, let's say you have some DAG, it just goes in one direction. And let's say that the longest part is D. Or for example, it has D layers. It has D layers like this. And this is S, this is T, right? Then you can find approximate max flow again, just because here again we have that any flow have average length at most D. So max flow have average length at most D. And you can solve this in MD over epsilon time. And some graph actually has small number of layers. Okay. So you can solve these 2 problems fast if D is small. But in general, even your graph is big, it's huge, and D it may not have small depth. It still makes sense to just try to compete with short flow, right? And when you just want that, in this graph, when you just want to compete with short flow, you can do it fast. And that kind of sometimes explain why push Relabel is used and fast in practice. Like many times, like you know that like there is just like short flow between them. That's the maximum flow. Just solve that. Okay. And you get maybe not maximum one, but approximately maximum one fast. But actually in practice, they are just fast, like an exact. So it has some other explanation. Yeah. It needs some other explanation why it's fast. Okay. Okay. So good. Next. Okay, so this is fast and nice, but you see that in general DAGs, the longest path can be as big as n, but we want to do better than mn. Okay, so here's the problem. You have a DAG, maybe with this topological order tau, okay. And we want approximate max flow. F star here is just max flow. What's the algorithm? Is this. It's short again, but the weight is similar but different. Any backward one, you set it to be 0. Any forward edge, instead of just set it to be 1, you set it to be big if the endpoint U and V of an edge are far away in topological order. Similar to shortest path, right? We just did this before. Okay. And we just run push Relabel with this weight function. And the tight, like how tight, like the slack in the tightness. Actually, I don't care too much. It can be like something like 0.5. It's not epsilon here. It's 0.5. And let's see first running time. Okay. The running time is going to be something like n squared times log n over epsilon. Okay. Why is that? Because this is basically the time for approx tight edge data structure, which we showed before that is like this running time. Okay. Push Relabel just take this running time. Okay. But why this is like n squared log n? We see this calculation before actually. Basically, like this thing, right? This is like a sum of the weight for the backward and forward one, but this is going to be at least the difference of tau in the endpoint. But the sum of this thing is n log n. You recall this, right? I will not go over it. Okay. So this thing is n log n, and h is just something like 2n over epsilon. This is actually important. We set h to be 2n over epsilon. So this in total is this one. Okay. Yeah, we use this fact here. If you recall, we used this in decremental shortest path before. Okay, but let me just tell you why the approximation is good. The proof is basically the same, except one thing. Okay. It's the same proof. I have a hash and I look at f1, which is like the reverse of minus f, and f2, which is f star. Just add them up and then analyze what's the weight of f of this sum, and analyze what's the value of this sum and get a contradiction. The same proof. But let's see what's the difference. Okay. We get this. The weight of the sum is just the sum of the weight. At most the sum of the weight. Okay. But now, here's the difference. We get this is 0, like before. But I claim that this part is at most n times this. Why? This is because, so just look at the flow F star in the DAG, right? The flow in the DAG go forward in the DAG in topological ordering. And let's look at each flow path. It might go jump quite a bit in DAG order or not. Anyway, it just go in this direction. But at each step, it only increase topological ordering. But the total increase in this tau in topological order is just n. And that corresponds to the weight, right? The weight of this path is just at most, it's just the sum of this, the weight of this forward path here. It's just a sum of this difference in topological ordering. This is at most n. So with this weight function, some edge can be long, but it's always, every path have weight at most n. So every path have weight at most n, and there are this many paths at most. And this is a flow, so there's like, yeah. So this is a flow, there's no, yeah. Like there's no flow path that kind of don't go to like that doesn't reach sink, right? There are this many flow paths, and each path have this length. Okay, so then we get that the length of f prime is at most n f star, and if for contradiction, if f is small, then we get that f prime has size at least epsilon f star again, and we get this. The average length is at most no epsilon. Okay. But now, good. Now we want the contradiction. We get now that like f prime is a flow in residual graph in GF whose average length is small. We want to say that that's impossible because the distance between axis and sink should be large. Okay. But how large? It's not going to be exactly h. We pay some slack here because we just use push Relabel with this. We use approximate type H data structure, right? So we only guarantee that push Relabel only guarantee that the distance from access to sink is at least h over some slack, which means that every path here must have length at least h over this slack. But this slack is like, you don't need this slack to be so small. Like this thing can be 1.5. So even if you set epsilon type to be 0.5, this is still like more than n over epsilon. And this would contradict, this thing and this thing would contradict each other. Okay, so that's contradiction. So you see that, okay, now on the DAG, we get faster algorithm. And it's similar to, like, kind of similar techniques to